In this lecture, we're going to talk about a particular skill, which is reading the output from regressions. Now remember early on in this course I talked about one reason to model is to be an intelligent citizen of the world, that there's just a certain amount of modeling understanding you have to have in order to get by, in order to contribute. Well, you might be doing some project, and what's going to happen is somebody's going to give you some sort of regression output that looks like this. And what you've got to be able to do is read it, understand it, know what this is saying. So we see some words on here we already know, right, like r squared. And we see things here like, say coefficient and intercept. What we'd like to do is be able to fully understand what output like this is saying. Okay, so the first thing to note is we've got to think about what's really going on. When we see regression output, what it really is it's a linear model, but it's a linear model based on multiple variables. So remember before we had y equals mx plus b, right? That was our model. It was a linear model where y depended on x. Well, what we're going to do now, typically when you see regression output, is that y, which is your dependent variable, depends on more than one. So it's like m1 x1 plus m2 x2 plus b. So for example, suppose, again, let's go back to the health example. Suppose y is health outcomes. Well, x1 might be how many hours of exercise you get, x2 might be how many hours of sleep you get, and so on, right? So what you've got is your dependent variable y depends on a lot of stuff. So when you look at regression output, like when you look at stuff that looks like this, you see there's more than one x. There's an x1 and there's an x2. Let's do an example to flesh this out a bit. Suppose again we're looking at student test scores, right? So that's y. That's our dependent variable. When it could depend on a couple things. It could depend on t, which is teacher quality, and it could depend on z, which is class size. So we just write down a simple linear model that says y equals c times t plus d times z plus b. B is, again, our intercept, right? That's just the familiar intercept before, just like y equals mx plus b. Now, when we think of this model, what should we expect? Well, what we should expect is that as teacher quality gets better, class size, or scores get better, so we should expect C to be bigger than 0. But we should expect as class size gets bigger, that the school performance or class performance should fall. So therefore, we should expect D to be less than 0. So when you see a model like this, one of the first things you want to do is you want to sort of come at it with some expectations, some preconceived ideas about what you think is going to be true. That way, when you look at your output, you can decide, is it surprising, right, or is it not surprising? So let's go back and take just a generic model where we have y equals ax1 plus bx2 plus c. So c here is going to be our intercept, right? That's our intercept. And a and b, these are the coefficients of our independent variables. And what we want to do is we're going to look at the output's going to tell us something about those coefficients. So here we go. Here's some regression output. Looks a little scary, but let's just relax a second. So let's look first and see what we see. First we see this thing that says r squared is 0.72. What is that telling us? Well, we already know. That's saying there was a whole bunch of variation in the data, and 72% of it was explained by our model. So that means a linear model, in this case, is explaining 72% of the variation. That's totally great. Standard error, 24.21, is telling us, on average, what was the standard deviation in the model. So how far from the mean were things? And this is telling us, on average, about 24. And then this observation thing, this 50, is just saying we had 50 data points. So we had 50 data points. On average, it was 24 away from the mean, and we could explain 72% of that variation. So, not a bad model. All right, now when we look down at this part down here, this whole part of it, this is telling us something about what our linear regression model is saying about the coefficients and the intercept. So the first thing we notice, this 25 here, is the intercept. And so that's saying our final regression equation is going to look like y equals something times x1 plus something times x2 plus 25. Right? Now this next term here, this 20, is telling us that the coefficient of x1 is 20. So it's going to be 20x1. And then this 10 corresponds to x2, right, plus 10x2. So this is just basically telling us our equation is y equals 20x1 plus 10x2 plus 25. Now let's go back to the previous example we were just talking about. Let's suppose that x1 was teacher quality. So this would say y, which was student test scores, are increasing in teacher quality. So that's what we'd expect. But suppose x2 is class size, and here we have a 10, and we get that test scores are actually increasing in class size. Well, then we'd say, this is sort of surprising to me because I expected class size to have a negative coefficient, and it's actually got a positive coefficient. So we might think maybe our data is wrong, maybe my intuition's wrong. So let's look a little bit deeper. So some things to look at. First is we should note we've only got 50 observations. So 50 observations isn't very many, so it could be that maybe these coefficients aren't right. Well, how do we know that? Well, this is where we want to look at this column right here with SE. SE stands for standard error. And what it means is it's sort of what's the error in our coefficients. So for example, here we've got a coefficient of 25, and it says the standard error is 2. So what that's meaning is, let's go back, remember, think of our bell curve. It's sort of saying our model is guessing that the coefficient of this thing is 25, right, that the coefficient is 25, but we've got a standard error of 2. So that means if we went between 23 and 27, we'd be right 68% of the time. So what it's saying is this 25 is a guess based on the data, and what this standard error of 2 is telling us is that, well, 68% of the time, we'd actually be, the coefficient would be between 23 and 27. So it's sort of saying, you know, maybe it's 25, but, you know, it's probably almost for sure between 21 and 29. Well, let's look at our x1. We've got a coefficient of 20, but the standard error is only 1. So what that's saying is we can be really sure that the coefficient on x1 is between, like, let's say 17 and 23. And we can be incredibly sure it's between 16 and 24. But now let's look at this last one, x2. The coefficient was 10, and the standard error was 4. So if I draw my bell curve, and let's go over here and draw a big bell curve here, make sense of this for a second, right? What it's saying is from the data, I'm estimating that coefficient of 10, but I've got a standard error, right, of 4. So that means there's a 68% chance it lies between 6 and 14, and there's a 95% chance it lies between 2 and 18, and there's actually at least a 2% chance it is, you know, below 2, right? So there's some chance that this coefficient actually, instead of being 10, could be negative. So you think, well, why don't they tell us that? And the answer is they do. So this column right here, this thing that says p-value, that tells you the probability that the sign is correct. Or I'm sorry, the sign is wrong. So what this is saying is there's no way those two signs are wrong. If you think about drawing this bell curve, we're getting an estimate of 25. There's no way the real coefficient is negative. But when we get down to x2, it's saying, look, there's about a 1.5% chance that this coefficient of 10, instead of being positive, it actually should be negative. So the regression output is saying because our standard error is so large, we're not sure about that 10, there's actually a decent chance of instead of being positive, that's negative. All right, exhale for a second. What have we got? So we see this regression output. It tells us a bunch of stuff. It tells us, first, what the R squared is. How much of the data do we explain? Second, it tells us how many observations do we have. Right? A lot of observations or not many. Third, it tells us how much variation was there in the data to begin with, and the answer is on average 24.21, so, you know, quite a bit of variation. Then it tells us the values of the intercept and the coefficient, right? These are estimates, 25, 20, and 10. And so it tells us, you know, this is probably positive and this is probably positive, and it gives us a sense of magnitude. So it tells us sign and magnitude. But it also tells us in this p-value thing how sure we are that those coefficients are correct. Now, it can't tell us, we can't be for sure it's 25, but we can tell us how sure we are that the coefficient is actually positive. And so here it's saying, we're really sure it's positive, right? Because there's almost no chance we're making a mistake. But for x2, well, there's a 1.5% chance that maybe there is a mistake there. So if this were, again, a regression of test scores on teacher quality and class size, what we could say is teacher quality definitely improves performance. And there's a lot of evidence that that's true. And we could say with class size, well, even though this study goes the wrong way, it's possible, since we only have 50 data points, right, that maybe if we did another study, it could go in the opposite direction. And that's true as well. There's a lot of studies on class size that do in fact show that as the class size gets bigger, students do better, even though that's sort of counterintuitive. But there's more studies that show the opposite, right? That as the class size gets smaller, students do better. So big things to take away when you look at that regression output. The first thing is look at the sign. Look at every coefficient and ask, does y increase or decrease in x? Now, before you look at it, when somebody says, oh, I've run a regression model, you should say, well, what are your variables? And then what you should do is you should form expectations about what you think the signs of those variables are, the coefficients are. Then when you look at it, you can say, does the variable have the effect that I thought it would have? So if you're looking at sales for your firm, you might want to say, well, geez, the coefficient on advertising is negative. The more we advertise, the less we sell. That would be totally counterintuitive, right? But if the coefficient on advertising were positive, that the more you advertise, the more you sell, then it would make sense. Then what you want to do is look at magnitude. You want to say, okay, how big of an effect on Y does a 1 unit increase of X have? And if it's got a big coefficient, that means, wow, this is something I should really pay attention to. And if it's got a small coefficient, it's something that maybe you shouldn't pay attention to. All right, so pretty straightforward, right? Regression output, all it's telling you is, right, how much of the variation did we explain, right? So that's a measure of how good the model is, and that's captured by R squared. Then it tells us what the sign and the magnitude of those coefficients are, right? So is the sign positive, and what's the magnitude of that coefficient? And then we also get that p-value thing, which tells us what's the probability that the coefficient's actually wrong, that maybe the data is so noisy we can't say for sure. So what's great is, if you've got data out there, you can throw that data into a linear regression model, right? If you've got an idea of what variables you want to include. And you can get some output, and then from that output you can get an understanding of, how good is the model, what's the R squared, what is the sign and the magnitude of the coefficients, and how confident can we be that those coefficients are right. So it's actually a really useful way for making sense of the world. And as we've shown in the previous lecture, right, it's usually better than we are at figuring out how the world's going to work. Thank you.